students, we are starting with the chapter Electric Current Through Conductors. That is chapter number 11 in your 11th standard. It is related to your current electricity. Basically, electric current through conductors. What we are going to learn? You know what is basically current? We have defined current in the lower standard. What is current? Current is a rate of flow of charge. It is a rate of flow of charge or flow of charge with respect to time, that is we can define as current. So already we have seen in the lower standard. Now in this 11th standard, let us go for the introduction part. As we have seen in the textbook, we are talking about an valence electron. What basically an valence electron is? You are having a valence electron. Suppose if I will tell you, if there is large number of conductors, we are having any metal, if we are going to take any metal, we are having a large number of conductors in this. We are having a conductor, and inside the conductor we are having large number of atoms. Suppose we are having large number of atoms. So I can just take, suppose these are the atoms we are having. So we are having a large number of atoms, infinite number of atoms, a very large number of atoms inside the conductor. And we are having, it's called valence electron, which is loosely bound to an atom, each individual atom, and the valence electron which is there, it is becoming basically delocalized. Now what is the meaning of delocalize? Delocalize. What is delocalize? The electrons becomes delocalized when number of atoms inside the conductor are very close to each other. So when the number of atoms inside the conductor are very close to each other, the electron become delocalized, means the electron will start randomly moving in all possible directions with all possible speed, with all possible velocity, that is direction. So basically what we are knowing, the valence electron becomes delocalized when a large number of electrons or when a large number of atoms comes together in a metal. So these electrons basically are nothing, it is your, you can tell it as conduction electron. So the electron which is there, it is called as a conduction electrons, and this is also a valence electron, but we are calling it as conduction electron because it is becoming delocalized when a large number of atoms are coming. So these valence electrons which was there, it becomes an conduction electrons which moves in all possible direction, with all different velocities or with different speeds. So when a potential difference is applied between the ends of the conductor, suppose we are applying a battery or a potential difference is applied between the ends of the conductor, this electron will start moving due to the electric field. The electron will start move in a particular direction. In the same direction, all the electrons are going to move, and hence they are going to they will constitute an electric current. So students, the topic which is given in your textbook 11.2, that is electric current. Electric current or current we will get due to positively charged particles and negatively charged particles. We can get due to anyone, that is positively charged particles or negatively charged particles. Now in case of gas, if we are taking the gas, inside the gas we can get current due to both positively charged particles and negatively charged particles. Inside a liquid we can get again the electric current is due to positively charged ions and negatively charged ions in liquids. And similarly in conductors, that is in solids, we are knowing the electric current is basically due to the flow of electrons. And we are having many other conductors. Like we are having semiconductors, we can get current in semiconductors due to again it is positively charged particles and negatively charged particles. So we basically get current. Here we are going to study basically about electric current in a gas. What happens in a gas, which is given in your textbook. Inside a gas, we are having positively charged particles which are randomly moving in all possible direction. And we are having negative charged particles, the gas, which are again moving in all possible directions. So as we can see, the net amount of charge moving in example forward direction is given by Q plus, and also you can take the net amount of charge moving in the net amount of negative charge moving in the forward direction is taken as Q minus. So positively charged particles we can take it as Q plus, and negatively charged particles we can take it as Q minus. So we are taking let Q plus with the positively charged particles, the net amount of positively charged particle which is moving in the forward direction, and Q minus is the net amount of negatively charged particles moving in the forward direction. So hence the total charge is given by the total charge, therefore can be given by is due to the net amount of charge flowing in this plane. Suppose we are taking this as the plane P. Flowing in the forward direction is given by Q plus, that is positively charged particles, and Q minus, that is negatively charged particles. Suppose we are taking the net flow of charge flowing in the forward direction, that is in the plane P. So Q is Q plus minus Q plus, that is positively charged particle, and Q minus negatively charged particle, and we are taking it as minus because net amount, example, it is flowing in the forward direction. Therefore the current is due to the flow of charge in a given time, that is I is Q by T. What is the unit of current? So current is rate of flow of charge, unit is given by ampere. So SI unit of current is ampere, that of charge is coulomb, and that of time is second. So here we can also tell that current is Q by T, 1 ampere is equal to 1 coulomb upon 1 second. Let I be the current varying with time. So let I be the current varying with time. Delta Q be the charge. Flowing in the plane. In given time, delta Q, the net charge flowing in the plane, is in this plane P, in given time T plus delta T, in a very short time, it is from T plus delta T. Therefore basically we write your current is at limit of delta t tends to 0 in the form of limit delta q upon delta t. So current is limit of delta t tends to 0. In a very small time there is a net flow of charge with respect to time. So I is limit delta t tends to 0 delta q by delta t. We can measure current when there is thundering in the sky, there is a light in the sky, that is, it may be very high, that is, you should know, it may be 10,000 ampere. And in your household circuit, we basically measure in form of few amperes in your household circuits, and we are having current, we can measure also in milliampere, microampere. Next is flow of current in conductors, that is 11.3, flow of current in conductors. What is there in this topic? That is 11.3, where we are talking about, we have seen the flow of current in case of gases is due to positively charged particles, ions, and negatively charged particles. Also in electrolyte, like liquid, the flow of current is due to positively charged ions and negatively charged ions. But you should know the flow of current in the case of conductors, that is metals, is basically due to the flow of electrons. So it is basically due to a negatively charged particles in case of flow of current in conductors. Okay, so when an electric field is applied to the conductors, we are knowing when the electric field is applied to the conductors, or as long as suppose if I am taking this an electric field, suppose I am taking this a conductor, and the electron was initially they was traveling in all, this electron which was there, it was traveling in all possible direction. This is the atoms which are present everywhere. The electrons was randomly moving in all possible direction. Okay, before electric field. Field before an electric field. So electric field, due to electric field, before electric field and after electric field, and after applying electric field. Now electric fields are applied due to what? Basically electric fields are applied with the help of your cells, that is battery, we can tell. And after electric field, when we apply electric field to the conductors, that is your battery, EMF, electromotive force, applying with electric field from positive to negative, all the electron which is there, it will start large number of atoms are there, and the electron will start moving from negative, that is from low potential to high potential. So when a steady electric field is applied, the battery is applied, the cell is applied, there is continuous flow of electrons from lower potential to higher potential. Okay, there is a steady flow of electrons, so there is a steady flow of current from higher potential to lower potential. So that basically we take it as conventional current. Talking about your drift speed, this topic we are having in 11.4. Drift speed is given by, it is Vd. We are knowing that again in the conductors we are having large number of electrons moving randomly in all possible direction inside the conductor. So electrons are moving in all possible direction. We have already seen electrons are moving in all possible direction. with all possible speed. So here the net flow of electrons, we are having the atoms which is there, the atoms are there and the free electrons are, this is the atoms, we are just in the red color you can see these are atoms, we can make large number of atoms are there, and there are valence electrons, there are free delocalized free electrons which are randomly moving in all possible direction with a very high speed. The speed is approximately, you can tell it is 10⁶ meter per second, it is very high speed we are having, 10⁵ to 10⁶ meter per second. We are moving with a very high speed initially when we are not applying an electric field. As we apply an electric field, what happens? As an electric field is applied to the conductors, that is with the help of batteries or the cell, all the electrons which was moving in all possible direction, they will, due to the electric field, they will start moving in the same direction from a lower potential to higher potential due to the battery, that is from negative potential to higher positive potential. So there will be drift, that is alignment in the direction of the electrons. So there will be drift in the motion of an electrons. These are the atoms we are just making here. And the free electron which is there will all start moving in the same direction, that is they are having a drift due to the applied electric field. Electric field is applied from positive to negative, and all electrons which is negative charge particle, they will start moving from negative to positive. So there is a drift in the electrons, large number of electrons, and all the electron which is there due to the electric field, they will move with the same speed, 10⁻⁴, approximately to 10⁻⁵ meter per second, which is very, very less. You can just see when electric field is not applied, when electric field is not applied initially, there is no current which was flowing here, but there is flow of electron which was there in all possible direction. And when electric field is applied and when batteries are applied due to electric field, the electron starts drifting, they start moving from negative to positive terminals, that is from low potential to high potential. So all of them now will have the same speed. Now they will have the same speed, and the same speed will be approximately 10⁻⁴ to 10⁻⁵ meter per second, which is very, very less as compared in the initial case when no electric field is applied. And when electric field is applied, the speed becomes very less, but all electrons are moving with the same speed. It is nearly about 10⁻⁴ to 10⁻⁵ meter per second in a particular conductor. Moreover, here what we can take, suppose if I will tell you, let L be the length of the conductor. Suppose if I am talking about here, it is L, let L be the length of the conductor. Now if I will tell you, let L be the length of the conductor, length of conductor, and small n, that is number of electrons per unit volume. So n is the number of electrons per unit volume. Suppose that is n upon Al. Volume is basically this area of cross section, entire area of cross section, that is uniform cross section we are having inside the conductor, and into length of the conductor. So if I tell you, let L be the length of the conductor and n is number of electrons per unit volume, okay, that is flowing inside the conductor, that is n upon Al. So total number, so if I tell you total number of electron which is there, that is, I can add, it is NaL. So number of electron which is flowing in this cross section area, okay, that is NaL. Now, so total number of charge which is flowing is total number of charge I can write. Charge is basically, it can be negative or positive, but here we are taking charge is basically defined as it is number of electrons into E, total charge which is flowing inside the conductor is Q is Ne, and hence here it goes like Q is N is nothing, it is NaL. Okay, total number of electrons that is flowing through the conductors entirely, it is NaLe. So here E is basically charge of an electron. So total number of charge, that is basically negative charge particle flowing through the conductor is N. Okay, that is number of electrons per unit volume into area of cross section and to length of the conductor into E is the charge of the electron. And hence we can tell the current flowing here is, but what is current now? Current is, we are knowing it is Q by T. That is rate of flow of charge. So current flowing can be calculated as, it is I which is equal to Q, that is NaLe upon time. But we know what is time. Time is basically distance upon speed. Velocity, if you will take velocity is distance upon time. If we write V is d by t, so time is distance upon speed. So distance is whatever distance it is going to travel, the charges are traveling from throughout the distance, that is length. So time is distance upon speed, and the speed they are having is given by Vd. That is which speed we are taking. Basically we are taking the speed that is drift speed of the electron. So T is L upon Vd. So we can write here as Vd is, therefore we can write that as Vd, that is drift speed of the electron is given by L upon T. So T is L upon Vd, and then we are having therefore current here we can write I, which is NaLe upon, here we can write time instead of time we can put L upon Vd. Vd is going to go up, you will get here current which is equal to, that is NaE Vd. So that's the relation between current and drift velocity. I is N, number of electrons per unit volume, and A is area of cross section, is charge, and Vd is the drift velocity. So here we are just relating current and drift velocity. Now again, if I am going to take what is my Vd also can be written as I upon A, and here we can write Ne, that is, suppose we are writing it is NaE. What I have done is Vd is equal to I upon NaE. Now if we are going to take your in respect to current density, but what is current density is defined here as, now we are just assuming what is current density. So current density is given by J. For having current density is nothing, it is current per unit area, that is called as a current density. So if we take drift velocity Vd, which is equal to I upon A, we can add J upon Ne. So now this gives a relation between drift velocity and your current density. Vd equal to J upon Ne. Here it is current density. Current density is current upon area. What is the unit of current density? It is ampere per meter square. So here we are having ampere per meter square is current density. So current density means current per unit area. So current is flowing per unit area, that is called current density. Here we have seen the relation between current and drift velocity. Here we are seeing the relation of drift velocity and current density. And hence also we can write what that is J, which is equal to NeVd again, or we can write here J is current density is equal to N, number of electrons per volume, is the charge of the electron, and Vd is the drift velocity of an electron. In vector form, basically, we can write J bar is equal to Ne, we write Vd bar. Now it means here basically current density and drift velocity are opposite in direction, because the electrons are basically, they are moving from negative to positive, we take, and so that is drift velocity of an electron. This is the drift velocity of an electron, that is from negative to positive. But current density, current, as we know, conventional current, it flows from positive to negative. So the direction of current density and drift velocity are opposite in direction, and E is the charge of an